So there's this skydiver problem. There's two of them, two skydiver problems on the back. Well, I guess we'll do the first one. Let's do the first skydiver problem. So here's what it says. You can read it with me, but a skydiver jumps out of an airplane. Here's the airplane. The skydiver jumps out of the airplane, and when they jump out of the airplane, they fall. Oh, by the way, they jump out with an initial velocity of 0 feet per second. And they fall, and there's no air resistance. All right, I'm sorry. Actually, what I wanted to do, and I might have done this already, but let's derive this equation. And I may have thought about this already. When you have a falling body, the forces that are acting on this falling body are what? Right, that force due to gravity. And that force due to gravity is called weight, and that force is mg. And then the other for a lot of calculus, you've ignored air resistance. But in this problem, we get to think about air resistance. And so there is some air resistance as you fall through the air. And so there's some air resistance, which is sort of friction in the opposite direction. And what we say is we assume that air resistance is directly proportional to the speed I'm falling. So this force of air resistance is directly proportional to the velocity at any moment. And that K is a proportionality constant. M is the mass, G is gravity. And that's the only two forces that are acting on this. And what we're going to say, we're going to call this. What's funny about this is we're going to call down positive and up negative. It's a little funny, but that's how we're going to do these problems.
The acceleration is coming.
So normally we call gravity some negative number, but we're not. We're going to call it positive in this case. We're just down is positive, up is negative. We're going to say. And then, in physics, what you do, and it seems like I've done this before recently, but in physics, you sum all the forces, and the sum of all the forces is equal to ma. So I'm going to say that ma equals the sum of these forces. This is my positive force, and this is my negative force, or it's this one plus this one, and this one's negative. We know that acceleration is the derivative of velocity, is the derivative of velocity. So I'm going to rewrite this as dv dt, right there, that's what A is. I'm going to move that kv over, and this is the differential equation that we are trying to solve in falling body problems with air resistance. It turns out to be this differential equation. I think in my problem that I wrote up for you, I said that. I did say that. Yeah, this is the differential equation. And when you solve it, watch out, there's a lot of constants in here. M is the mass, that's constant. K is a constant of air resistance somehow. G is gravity. So the variables are V and T for time. And I guess when you solve this dE, you'll have V. You'll have the velocity of this falling object. When you solve this differential equation, you'll have V, the velocity of this falling object. Okay. So that's the differential equation. We could sit here and solve it in general. The book has an exercise that wants you to do that. The book has a problem number 35 that just says, go solve this in general with M's and K's and G's, and you can do it. We could do it, but I'll fill in the M's and K's and G's. Let's go back to the skydiver problem then. So the skydiver falls. He's got this initial velocity, and then he falls. And when he first falls, he has no parachute. And with no parachute, you can tighten up in a ball, and you can have not very much air resistance. You can really book it through the air without a parachute. And so what it says is for the first little time there, you got to read through that whole long paragraph, but before the chute is open, before the parachute is open, K is 0.4. And by the way, it says it's going to fall for 12 seconds. So K is a 0.4. And this skydiver is going to fall for 12 seconds. So then at 12 seconds, bless you, we open the parachute. After we open the parachute, we have a lot more air resistance with that big parachute over our head. And now the K is 12. Wow. Now the K is 12. So this is before the parachute opens. And this is after the parachute opens. Right. All right. It also says that the mass of this person is 4 slugs. So in this particular problem I made up, the mass is 4 slugs. That is what it is. And you guys know that? You know, force can be thought of as mass times acceleration. You know, when your acceleration is feet per second squared and your force is pounds, then your mass is slugs. That's a true unit. Usually you're used to the metric units, I guess, where your acceleration is meters per second squared, and your mass is kilograms, and your force is measured in newtons, right? You're more used to that, but when we're in these units, and a lot of math classes are in these units, the mass is called slugs. And gravity is 32 feet per second squared. Gravity is 32 feet per second squared. And we're going to call it positive. Hey, so do you know how much this person weighs? 4 slugs, 32 feet per second squared. Is gravity 128? 128 pounds. Yeah, that's how much this person weighs. 128 pounds. All right, well, I think I want to try to solve this DE. Where is it? Here it is. You know, you might think of this as a piecewise problem. You might think, okay, before the parachute opens is the first 12 seconds, and then after that there's another scenario after the 12 seconds where they open the parachute. And you could treat it like a piecewise problem. The truth is that's not the way we're going to treat it. The book suggests we do it as 2 separate DEs. We really we work on that first 12 seconds, and then we totally just restart the problem as a new DE. And we restart time, and we restart our height, we restart everything. By the way, what was this initial height up here?
0. 12,000.
Oh. Okay, it was 12,000 feet, but you might be onto something when you called it 0. You might be onto something. Because I've gotten everything backwards.
Plus and minus.
I might want to call the ground 12,000. I might want to call that 0. But hang on, we're a few steps away from that. Hang on, so here's my DE. I want to fill this in and solve this DE. My mass is 4. Is that what we said? I'm going to move up here. The mass is 4. dV dt. The K is what's the K here? 0.4. And this is the 4 times the 32. This is the 128. How you guys doing? I just took this DE and filled the numbers in there. And now we can solve a little DE. Step 1. Oh, by the way, sorry, there is an initial condition. At time 0, what was the velocity? 0. Yeah, that's this person just stepping out of the airplane. They didn't jump down. They didn't jump up. They just casually stepped out with an initial downward velocity of 0. Well, you know how to do this, I suppose. Divide by 4. Divided by 4, divided by 4. dV dt is plus 0.1 v equals 32. I would get the integrating factor, which is e to the 0.1t. You guys with me on that? That's your integrating factor. You multiply through by it. After you multiply through by it, this becomes e to the 0.1t times v. Over on the other side, it's 32 e to the 0.1t. Not too bad. I would integrate both sides, I suppose. Integrate both sides. All right, e to the 0.1t times v equals, when you integrate this, you spit out a 0.1 out into the denominator. I think I get 320 e to the 0.1t plus c. You guys agree? Thank you. And then I divide by this e term, and I guess I've already solved this dE. That wasn't too bad. I get 320 plus c e to the negative 0.1t. And with my initial condition, I can find c. But that's a good old integrating factor method. Not too bad there. With my initial condition, I can find c. My initial condition says when t is 0, v is 0. I'll just plug that in. Oh, that's e to the 0, so this is c. So c is negative 320. So here I am. My velocity for the first 12 seconds is, here I am right here, 320 minus 320 e to the negative 0.1t. Ta-da! We solved the dE. Now, we got our work cut out for us. By the way, I never did ask the ultimate question. You know what the ultimate question is? It's written on your paper. The ultimate question is, we want to know, how long was this trip? If you say more than 12 seconds, you're correct. But she's going to fall for 12 seconds. She's going to open her parachute, and she's going to float a while before she hits the ground. Anyway, the question ultimately is, what is the total time of this trip? And if that's the case, then I do need distance in this problem. And so I need to get to distance. And the way I wrote this problem, I gave you a hint there that says, if you've got a velocity equation, how do you get from velocity to distance? You integrate. And it's not a complicated dE, it's actually just an integration. So I think I'm going to need that. I'm going to need what we call distance, or S, and I need to integrate this. Here I am, I'm going to call it S, and I'm going to integrate. Integrate a 320. 320t. Wow, integrate this. I think it spits out a negative 1.1, a 1 over 0.1. Negative 1 over 0.1, I think I'm going to get positive 3,200 e to the negative 0.1t. And guess what else?
Plus c.
Thank you. Another plus c, a different c. Huh. So in order to find this c, I do need an initial condition about my distance, about my initial distance. And we're going to say that at time 0, the initial height was 0. That is what we're going to do. We're going to call this initial height 0. We're going to call the ground 12,000. Why is that?
Because if our acceleration is in a positive direction, right, we don't want, because that would make the height negative again. Since we're falling, we switch the signs.
I don't think it's height, I think it's distance traveled. So at time 0, it's you travel 0.
But because I think you're both on something there. I think you're right. Because gravity is downward is positive, as I fall downward, I have a positive acceleration. That's going to make me have a positive velocity, which means, and a positive velocity means I'm I'm gaining distance as I fall. I'm not losing distance as I fall, I'm gaining. So I want to start with calling this 0, and when I hit the ground, that'll be called 12,000. Okay. All right, we've convinced ourselves. Thanks. What do I do now then? Use this initial condition to find C. Use that initial condition about the distance to find this C. If you plug in a 0 for time, you get 0 for S. And if you go through those motions,
C negative 3200.
you get 0. That's a 0. You get a 3200 right there. You're right. Plus C. The C turns out to be negative 3200. You're right. Yep. If you don't mind, I'm going to drop this down here and just put this in that spot there. Sorry about that. Negative 3200. And I'm going to put that in a box. This is awesome. This is awesome. Hey, you know what? I guess I need, like I said, now here we are at 12 seconds. She opens her parachute. And what changes? When you open your parachute, what changes?
Air resistance constant.
Thank you. Your K. Thank you. Yeah. Yep. Your constant of air resistance. Yeah. That's what changes. So now I got a new problem. And so I just redo this whole problem. I want to start time over. I want to start the velocity over. I'll have a new height. Yeah. So it wouldn't be that hard though, but again, I got to do this whole thing over again. But hang on now. So for this new problem, let's write it up here. It'll be 4 dv dt, and you're saying the k is now a 12 v equals 128. But you know what I want before I proceed with this new problem? I want my initial conditions for this now. So if we're restarting time, then now at time 0, what's my velocity?
Plug it in.
Good. My starting velocity for this second part of the trip will actually be the ending velocity for the first part of the trip. So I need the velocity at 12 seconds. You're right. And I got a velocity formula here that's valid for the first 12 seconds. So I need the velocity at 12 seconds. That'll be my new initial velocity. If you can plug in 12 and help me out, I'd appreciate it. The velocity at 12 seconds.
I don't know if I'm right, Justin. What would you get? Yeah, you guys are right.
All right. 223.62.
223.62. All right, I'll just go with the 0.6. So that's the velocity at the moment I opened my parachute. Then I opened my parachute and I experienced this huge jerk. But that is the initial velocity for this part of the problem, right? 223.6. Okay, cool. What about the distance? I want to know the distance I've fallen. I guess this is the distance you've fallen. I think I want to know S of 12. I would like to plug a 12 in here. If you could help me, I'd appreciate it.
Could we not just make it 0 again?
You're right. I still would like to know this distance I've fallen, but you are right.
1,603.8.
1,603.8 feet. That's how far I've fallen. Okay. But he's right. We're starting this problem over. We're starting time over. We're gonna restart the we're gonna call this S equals 0 now. And if I'm gonna call this S equals 0, then
Subtract the bottom part.
thank you. I'm gonna have a new ground. Right. My ground will now be S equals, subtract the 1600 from that, 10,396.2. Okay, that'll be my new ground. And you're right, I'm not really using this number. I mean, I needed this number to calculate my new ground level. But I'm going to go over here and use an initial condition that says S of 0 is 0. So I'm restarting time, I'm restarting the height, but I do need this initial velocity. That totally makes sense. I do have an new initial velocity now. You guys okay? This is the procedure for this problem. I'd like you to know it. You can practice it a few times. I'm gonna ask you to do it in class. This will be on your in-class test. It's not on your take-home really, except in the practice form. All right, I'm gonna do this again. Maybe I should memorize the form, but I'm just gonna do it because it didn't take too long. I'm gonna solve the DE. I'm gonna divide by 4, divide by 4, divide by 4. dv dt plus 3v equals 32. I need the integrating factor, e to the 3t, I guess. Multiply through by it. You get e to the 3t times the v. And over here you get 32 e to the 3t. You integrate both sides of this equation now. You integrate both sides of this equation. On this side, e to the 3t times v. On this side, 32 thirds e to the 3t plus some c. Divide by that e to the 3t, and v is 32 thirds plus c e to the negative 3t. That's pretty cool. If I use my initial condition, I can find c. Am I talking too fast? Is there anything you would like to ask me or interrupt me? Or that was not too bad to solve this little DE with the integrating factor method. Using the initial condition, this is a 223.6. This is 32 thirds, and this would be a C when you plug in 0. So you're subtracting the 32 thirds, which is 10 and 2 thirds.
212.9.
212.9. Okay, thank you, that's C. So my velocity equation is right here, 32 thirds with the C plugged in, 212.9 e to the negative 3t. Awesome. Now what, you guys?
Integrate again.
Oh, integrate to get position, yeah, or S, or height, or position, yes. Integrate to get position. Okay, so S is the integral. 32 thirds t, that's how you integrate. When you integrate this e function, you divide by a negative 3. It's okay to decimalize it. Negative 70.
0.97.
71.0. If you're rounding to one decimal, 71.0.
All right, I'll take 71.0. Because that's practically a 213, huh? 71.0, I'll take that. E to the negative 3t plus another c. Okay, remember we called that initial height 0 again, so I can use that, plug that in. When I do, I'll get 0 here, no, that'll be 0. I'll get a negative 71 plus c, so c will be the positive 71. If you don't mind, I'll just plug that in. This is awesome. This is awesome. So now what?
You want to find out when it hits the ground.
I want to find out when it hits the ground. And normally, I mean my whole life, when something hits the ground, you set it equal to 0. Sorry, we called this 0. And the ground is 10,396.2. And so I should set it equal to this and solve for t. What's a little funny, watch, I'm going to do that right here. 10,396.2 equals that final distance equation there. 32 thirds t minus 71 e to the negative 3t plus a 71. And we want to solve for t. And I don't know how long you're going to stare at that before you realize maybe, yeah, you know, I don't know how much you realize about algebra, but when you've got algebraic functions kind of mixed with what we call transcendental functions like e's and logs and sines and cosines, but when it's mixed with algebra, you can't really solve it. I mean, I can't, there's nothing, I can't get t by itself with this algebra mixed with this e stuff. There's just no algebra I can do to really get t by itself. So at the end of this problem, we need maybe a graphing calculator can help me solve it. This is old pre-calculus graphing calculator idea, but I think I would put in my graphing calculator y equals 10,396. That would be a horizontal line at 10,396.2. And then I would type this in my graphing calculator as a function. And I would see it cross, and then I want to know when do they intersect. And I want to find that time. So I guess you have to do that in class. If this kind of problem is in class, at the end of this problem, you can't actually solve. You need a graphing calculator to solve it for you. Use technology, use a graphing calculator. In order to see where they intersect, you need to set your window big enough. Listen to this. She's probably going to fall for 10 minutes. 10 minutes is how many seconds? 600 seconds. So set your window all the way out to 600. Maybe she falls for 20 minutes. Maybe out to 1,000 or 1,200. If you set your t-axis out to big enough, then you'll finally see this point of intersection. But t is in seconds, and she's probably going to fall for, I don't know, maybe 5 or 6 minutes. Maybe it's only 5 or 6 or 8 or 10 or 10, 12 or 20. I mean, it could be anything. I got several different problems with different numbers. If you're going to go skydiving, it'd be fun to hang out up there for a while, you know. Kind of float down slowly. Anybody got an answer?
No.
Yeah. I mean, you can, again, you type that into your graphing calculator.
You want to find that point?
Maybe you type, on your Y window, you set it to 11,000 or something. You'll see this horizontal line. 168. 968. That might be. 968 seconds. Okay, cool. You found it. Yeah, that's good. That's good. We're finished. I mean, so the total trip, at the end it's a little calculator exercise and then you're done. The total trip is actually the 968 seconds plus the original 12 seconds, right you guys? So 980 seconds would be the answer. What is it? That's 16 minutes. I think 16 minutes and 20 seconds. I didn't really get it. Well, I did have a confirmation. I had 2 people say 968, I guess. I'm getting more people?
Let's see.
Okay. Okay, good. All right, that's a cool problem.
Intersection 967.9875.
Yes.
All right,
Okay.
968. All right.
Nice.
Yeah, that's a nice problem. I like that. I like it. I like it enough, so I'm putting it on the test. I don't know. I'm getting better at it. I used to seem like it was a harder problem, but it doesn't seem that hard now. But it's lengthy little problem. And it's got some good ideas that you have to think about. Cool. So you could practice this one again, but maybe that's, there's another one right below it that you could practice. I'm a little worried on that next one I wrote. She falls for 28 seconds before she opens her parachute. So it's probably okay, but I'm hoping,
She doesn't go splat.
yeah, I'm hoping, I wasn't trying to hurt anybody. So there's no telling.
In that case, you would just plug the time of the original equation, right? If your distance was bigger than the height of the cliff, she would have hit the ground.
Right.
Gotta find a winch.
Or the plane.
I guess you would find that out because you would try to find this time, right? Hopefully it's not past the ground, right?
Or like the surface area of the splatter.
Yes.
Did you actually have to find the first distance?
Let's see. Because I restarted it, everything started over, time started over, velocity started over, so my distance had to start over.
You needed the velocity equation to plug in to find the initial, but you didn't really need the distance of the first part. What do you do?
Well, I needed, so this distance though is only valid from here down. That second distance equation is only valid from here down. And I needed to set it equal to that displacement, which was that, I needed this number. Which means I needed that other number, right. I did, I guess. Yeah, it sort of feels like you didn't, but yeah, you did. Okay. Well, that's good. There's other good problems we can practice from the book, or I could ease into this other, let me do this other new idea here. If I go into 3.2, there's really only one idea I want in 3.2, and I'm not sure if the problems I assigned, I'm not sure if the textbook problems in 3.2 are exactly what I want. But here's the deal. In 3.2, what we want to talk about is this logistic model. It's called the logistic model of population growth. It's pretty interesting. Watch. I'm going to give you this discussion. Okay, this theory here a little bit. Normal population growth assumes that the rate at which the population is growing is directly proportional to the population at any time. Normal old population growth, it says this. And then we solved this DE, if you recall, and what was our answer?
Must B equals CE to the KT.
Right, this is good old classic population growth. The rate at which the population changes is directly proportional to the population present at any time, and the solution is good old, it looks like this. Which, by the way, when you graph something like this, it's just kind of crazy exponential growth. So, just unbounded growth. All right, so maybe that's true for certain populations, certain times, but maybe this is true also, that as the population grows, listen to this, as the population grows, maybe that K doesn't remain constant. That rate, that proportionality constant could become a variable. And they're saying that maybe as the population grows, that K, that rate of growth, becomes smaller. So now all of a sudden this K is not a constant. And so, and what we just said is that maybe it's decreasing. Okay, that's what we just said. It's not increasing, it's not constant. We think as the population grows, we think the K is going to decrease. All right? I don't want to explain every little number here, but watch this. This is a decent explanation. I'm going to put population on the x-axis, and I'm going to put K on the y-axis. What I'm saying is, as the population grows, the K gets smaller. So decreases. Now, when we say something decreases, your book does this. Your book said, well, it can decrease concave up, it can decrease concave down, but for simplicity's sake, let's say it decreases linearly. I mean, you're decreasing. So you can try to model how you decrease, but we're going to assume that it decreases linearly. And then they put some numbers on here, but I'm just going to jump to the point here. What you have is a decreasing line. This K becomes this, A minus BP. Now, does that make sense to you? Look at this a second. If this is K, on this picture, you've got kind of a y-intercept, maybe of A, and you've got a slope that's, your P is acting like X, and you've got a negative slope, which means you're decreasing. I mean, I'm not really explaining every little A and B here, but this is a linear equation with a decreasing slope, or with a negative slope. So this is So, all of a sudden, this model turns into this model. I mean, that K that was a constant, it has been modified to be this. And this is the famous logistic model, is this. And it's famous, and you've already dealt with stuff like this. You saw something like this back in chapter 2 with some numbers in here. You solved it. If you actually clean it up and look at it, it's Bernoulli is what it is. And maybe we should attack it with a Bernoulli to solve it. We should do Bernoulli on it. What I'd like to do is throw some numbers in there and do a real problem. I also want to say this about the graph. These are beautiful. You saw these graphs when we were doing some of our phase portrait analysis and slope fields. Because what this is it's population growth. But look, what did we say? What did we say was going to happen to K? The rate of growth is going to decrease. Now, that doesn't mean the population is going to die out, but the rate at which it's growing is going to decrease. And so we end up with this model. It's decreasing at a lesser and lesser and lesser rate. I mean, this is what the solution to this DE is going to look like this.
So is there a limit?
There is. Yep, there is. This is called the carrying capacity of the environment. I mean, maybe that's what causes this population to begin to slow down. I mean, there's only so much mosquito larvae in a swamp. The frog population, there's only so much food to sustain the frog population in the swamp. And so the frog population might be limited by that Y value, and that Y value is called the carrying capacity of the environment that you're in. I'd like to try a real problem, which means I'd like to just make up an A and a B. That's a little tricky. I've got one on your piece of paper, but that's your take-home problem. I don't want to do it for you, but I'm going to do this for you, which is similar. Let me see here. So I'm going to put 4.4 minus 0.00 0.05p. That's my A and my B. I made up. Times another p. I made up this problem. But it's this differential equation. Let's pretend it's frogs in a swamp. Let's say the initial amount of frogs in the swamp was 20. I made that up too. And now I have a DE I'd like to solve. Yes. So
What are A and B in like English letters? How do we find?
you know, they're just some constants that came out of my discussion of how to manipulate K to be not constant, to be decreasing. There was just some numbers I came up with to.
I meant like.
I know I don't have a good physical meaning for them. I don't.
Okay. So like if we were reading a word problem,
Right.
what we know is A.
In this kind of word problem, we just give you the DE, I guess. We don't
Okay.
make you derive the DE. We gotta give you the DE.
Yeah.
And it has numbers similar to these kind of numbers, I guess.
I see it. Okay.
Yeah.
It's right here.
Distribute.
Yeah, okay, we want to solve the DE. He's right, I should distribute the P. After that, I think I'll move this term over, so I'm going to do a couple moves in my head there. That'll be a negative 4.4p. And over on the other side, I think it's negative 0.0005p squared. Is that what that is?
Yep.
And that is classic Bernoulli. You can solve it with the appropriate substitution. It's really not that hard. You should let u equal p to the -1 because it's 1 minus n is what you're right. It's 1 minus 2. You're right. P to the -1. So what's du dt? Du dt is -1 p to the -2 dp dt. And maybe we remember how to solve this. I would multiply through by the -1 p to the -2. That forces it right here. When I multiply by -1 p to the -2, this becomes positive 4.4 p to the -1, I think. When I come over here and multiply by -1 p to the -2, it becomes positive 0.0005, and the p to the -2 kills the p squared, so that's awesome. What happens after you multiply through by that is this is what you need. What is this? This is du dt, and that's 4.4u, and that's that. And we have a little dE to solve. Find your integrating factor, e to the 4.4t, multiply through by it. After you multiply through by it, the left-hand side becomes e to the 4.4t times u. On the other side, it's a 0.0005 e to the 4.4t. Integrate.
Yeah.
And then that right side.
Is 0.0005 divided by 4.4.
Yeah, you got to divide by 4.4. Wow, that's going to be small, huh?
Yeah.
1.14 times 10 to the -4 if you want a decimal.
All right, so hang on. I might just leave it as 0.0005 over 4.4 e to the 4.4t.
Plus.
Oh, thank you, plus c. divide by this E term, and U equals that number. You know, I'm just being a little weird because I'd like to not make this some weird decimal and lose it and round it off. I'd like to try to keep it an exact answer. And you know, here's one way to do it. Can I multiply the numerator and denominator by 10,000?
Yeah.
If I multiply by 10,000, that means I'm moving the decimal over 4 places. So I get a 5 over, if I move the decimal over 4 places, I get 44,000. That's the number y'all got in your calculator, I guess. Which, by the way, reduces, but let's just move on here. What am I doing? I'm dividing by e to the 4.4t. I just rewrote that fraction, and I get c e to the negative 4.4t. If you divide a 5 out of that 44,000, you can make this, by the way, hang on, what's u? What's u? What's u? What's u?
U is p to the negative.
It's 1 over p. Yeah, p to the negative 1. So there's u. I'm getting back to p here. The 5 over 44,000 is actually 1 over
1 over
8,800?
Yep.
I'll be darned. 1 over 8,800 plus c e to the negative 4.4t. What do I do now?
You're going to use your initial condition.
I think I will use my initial condition. Right now, I could solve for p, but I could do it right now. What is mine? Here it is. My initial condition says when t is 0, the initial population of frogs is 20. So 1/20th equals 1/8800th plus c. Subtract right there. You know to subtract, I hope. And c would be whatever that is. 1/20th minus 1/8800th. And I'd like it as exact as I could get it.
439 over 8,800.
Oh, good. Say that again.
439 over 8,800.
Wow. This is awesome, you guys. So where are we? We're getting there. Coming back over to this side, the answer is, well, it's 1 over p, and it's 1 over 8,800 plus that c, which you said was 439 over 8,800, e to the negative 4.4t. Hey, we really want p. So I can reciprocate the entire side, and p will equal the reciprocal of this. Now, look, they're both over 8,800. If you don't mind, I can make this one big fraction over 8,800, and if I reciprocate it, I'll have 8,800 in the numerator, and 1 plus 439 e to the negative 4.4t here in the denominator. And this is a good-looking answer. If you type this in your graphing calculator, it looks like this. They both had the denominator of 8,800, so
Yeah, it was 1 plus.
I thought of it as, yeah, it was a
Yeah, I
plus.
got it. Okay.
Reciprocate. That's what you said. That's what I said. I said.
Can you see the carrying capacity on this? Can you see what the carrying capacity is? It is the 8,800. How'd you know that? Did you know that? That is the carrying capacity. Here's how you could calculate it. You could say to yourself, the carrying capacity is the population that you are going to eventually approach as time goes on forever. Thank you. So if you took the limit as t goes to infinity, that's the carrying capacity of this environment. And it's easy, watch. When you take the limit as t goes to infinity, that's a negative infinity. E to the negative infinity is a 0. This zeroes out, and the answer is 8,800. And so that numerator, when it's in this form, that numerator is known as the carrying capacity.
What is T in?
What is T? It's time. I didn't do a great job of describing this problem. I said it's frogs in a pond. I said we started with 20 frogs. I could say time is days. That might not make sense. Months.
So you don't say 4.5.
What?
Just 4.5 T equals pretty much that.
So hang on, what did you just say? A small amount of T. You said 4.5? T does what?
Pretty much gets it at its carrying capacity.
Gets you close to 8,800, huh?
Right on that. Pretty close.
Okay, now really, again, you never approach 88. I mean, you never get to 8,800. But you do get close rather quickly is what he suggested. In 4.5, he tried something. He tried plugging in a T, I guess, or he graphed it on his graphing calculator, looked at it. See, now that I know that, maybe I'll make T years. Maybe I'll make T years. I don't know. Now that I know the answer. Yeah. There should be some of these problems in 3-2, but they don't make them quite as clear as this.
The graph is like super steep, and then it just kind of gets there.
Yeah, so keep in mind I made up my A and my B. So right, it might be more of a gradual thing here, but you're saying
It's super steep.
it's steep. It just
Yeah, just like pretty much. Yeah, just like that.
yeah, I got you. Okay. Because it had to go from 20 to 8,800, and it did it in a short amount of time. That must have been dictated by my A and my B, I guess. No, we could play around a little smaller. Anyway. Yeah, interesting. This wasn't a long, drawn-out process, right? Their population exploded. They ate all the damn food, and then they had to taper off. Right.
I feel like you could skip half the question, like, and just go directly down some. Actually, you go way down even over there, because as long as you know the 4.4 and the 0.005,
You're on to something. I mean, I'd like you to solve this. I want you to solve it. In the book, the book's kind of funny. I want to show you what the book. So the book says this is the DE. A minus BP times P in general, that's the DE. And then, they say at some initial time, we have an initial population of P naught. And then they solve this in general without numbers, and they get to this answer. Hang on, watch this. This is their answer. A P naught over B P naught plus A minus B P naught e to the negative AT, e to the negative AT. Now, so what I don't really want you doing is grabbing your A and your B and your P naught and throwing them. I mean, anyway, on my take-home thing, I'd like you to do what I did. I'd like you to solve the Bernoulli DE.
I mean, at least you have a way to check it.
But you can check it with this. Now, the truth is, this form that they left it in is not the form we get here. I want to show you something. want to show you something. To get to my form, here's what, to get to my form, which is kind of the form that you get when you do the Bernoulli DE, you do it, you end up kind of here. What you want a 1 right here. And you can get a 1 right there if you divide everybody by BP0. Divide top and bottom of this equation by BP0. And then you'll get, in the numerator, what will you get? A over B. And by the way, that's your carrying capacity.
Yeah.
It is. And then this will be a 1. And then this will be kind of complicated looking, I suppose. But in general, this will be the answer. But then you're right. And then when it's in this form, this number is the carrying capacity.
So you can just plug in all the, what we know and find it.
Well, you're right. We do. We know A, we know B, we know P0. You're done.
What do you want us to do?
Well, on this take-home thing, I'd like you to run through that one I've asked you to do. Right. I'd like you to solve it. I think my directions say that. Please actually solve this. By solving the differential equation, yeah. By the way, this is my little take-home thing. What are my questions? My questions are, solve the DE, that's part A. Part B says, find the carrying capacity. Well, that's been explained to you. I guess you know how to do that. Part C says, find the population after 8 years. Can you find the population after 8 years?
Plug in C.
Plug in an 8 for T, right?
I'm assuming that's going yearly.
Yeah, I know. It is, in my word problem, it says that, I guess. Yes.
It might be like.
It didn't even say years, but it is. And then there's this question. This is another interesting aspect of this logistic growth model. I got this question. At what time is the population growing most rapidly? Look at this picture. When is it growing most rapidly? Growing most rapidly.
The population's half compared to the carrying capacity.
Well, you're right. When is that? Yes. Yeah. It's growing. Look, it's growing at a faster rate. It's getting steeper. It's getting steeper. It's getting steeper. As soon as it hits the inflection point, it changes concavity, though, and gets less steep, less steep, less steep. So the point at which it's growing the fastest is at its steepest slope, and the steepest slope happens at the inflection point. Now I'm asking for that time. I'm asking for that time. But if you heard what he said, and this is always true on these logistic models, that I'm asking for that time, but that time always happens at half the carrying capacity. 1/2 the carrying capacity. You hear me? Did you guys catch that? I think that's an interesting proof. How would you prove that that's the inflection point? Oh my God.
Let's like test around.
I guess you might need a second derivative. Yeah, good luck.
Second derivative and test
You
around.
could find a second derivative. You could look for the inflection point by looking for when the second derivative is 0.
Oh, okay.
But it always happens at that y value. The y, I don't know what the t value will be, but the y value is half the carrying capacity.
So only the first pages, the questions for those. We don't-
Yes, yes. And what we're talking about right now is question 3, I guess. Yeah. Listen, so the question is, when is it growing most rapidly? And you're allowed, you don't have to go do a second derivative and prove, you don't have to do a second derivative and find an inflection point for me. You don't. We can assume that we know that. Somebody told us that. And so if I'm asking for that time, then what do? You set this equal to 4,400, right? We're going to use that as given knowledge. that it happens. I'm asking, when is it growing most rapidly? It's growing most rapidly when the population is half the carrying capacity. And then I'd ask you to solve for time. I'm looking for the time when that happens. You know, this turns into an algebra problem, you guys, but it's kind of fun. If you multiply by this denominator, after you multiply by this denominator, you know, what's the first thing I want to do? Divide by 4,400, which will give me a 2. That'll always happen. And then I'm left with this. Are you guys following me?
Yep.
Subtract the 1. That'll always happen. I'll get, moving way over here, 439 e to the negative 4.4t equals 1. Divide by the 439. 1 439th. Take the ln of both sides. Oh my goodness. I don't even know if ln can go that small. And then divide by negative 4.4. I was making a joke. Divide by negative 4.4. This is interesting. It's some amount of years, and it wasn't long. You guys told me this thing got steep as hell very quick.
1.38.
What is it?
I got 1.38 years.
Wow. 1.38 years. Yeah, that's nothing.
That is really low.
So, the population after 5 years go to like 7,799.9 or something like that.
Close to the carrying capacity. That's after 5 years. You know, after 10
Way out
years,
there.
I mean, the rate at which it's growing now is not very much. So after 10 years, it probably didn't change too much more. And after 15, 20 years, I mean, but anyway, at some point it's 8,600, 8,700. Another 30 years and it's 8,750. I guess. Right. Hey, we'll quit today, I guess. But I'm good. I'm happy. I got through a couple of ideas that were lingering in chapter 3 that I wanted you to know. I don't have too many more lingering ideas. I'd love to help you with homework. So if you got some questions Thursday, maybe I could clarify something on the take-home quiz. I don't really want to do the take-home quiz for you. But I could help you with some homework in the book or any problems you want to talk about Thursday.